Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Operations Research in Multimodal Transport Towards Cleaner Ports. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. One of the needs that must be met to have a sustainable world, that can cope with the problems arising from an increasingly large world population, are sustainable ports. To achieve this, three fundamental problems must be faced. First, energy efficiency, integrated analysis of minimizing the cost of energy supply and minimizing environmental impact. It is a bi-criterion problem, since the two minimizations move in opposite directions. It implies redesign of the energy supply chain to the port and its ecosystem, including all available power technologies. Simulation of the optimal integrated operation of port operations and energy supply. Implementation of a smart grid to handle integrated port operations and energy supply planning and scheduling. Second, port region integration, integrated analysis, through a regional planning model, of the relations between the port and the region, to develop actions on the territory that improve the quality of life in the port region ecosystem. It implies implementation of a regional planning model that includes the impact of the port in the region. Analysis of the main port region problems. Integration of multimodal transport services for containers and bulk materials. Third, environmental control of the waterport ecosystem, integrated analysis of the pollution processes of water bodies and determination of the actions that must be taken to maintain the ecosystem environmentally sustainable. It implies implementation of a finite elements pollutant dispersion model in the aquatic system. Implementation of an optimization model that integrates an optimization algorithm with the simulation of contaminant dispersion. Remote information capture to project the boundary conditions of the body of water, in space and time. Weather planning of the trip on the boat. Three aspects must be taken into account in fuel consumption, and therefore in the emissions generated. Tidal height, wave height, marine currents, and motor speed, depends on the type of motor. Additionally, the characteristics of the boat must be considered, including the dead weight and the additional load. The wind speed and the water speed are determinant of the ship's speed and therefore fuel consumption. In practice, it is one more variable to control, which is directly affected by hydroclimatic conditions in the sea. Any weight for a ship is related to the sub-optimization of the speed of travel. Going full speed, to be on time, can also involve under-optimization. To quantify the importance of what we call trip weather planning, the best solutions from the selected test instances for both mixed weather and bad weather scenarios are compared with the performance of the programs performed assuming good weather throughout the planning period. The article, A Time-Dependent Vessel Routing Problem with Speed Optimization. Introduce the mathematical model. Time-Dependent Vessel Routing Problem with Speed Optimization, TSO. Used in Norway for route and speed planning of ships visiting North Sea platforms. It should be borne in mind that, from the point of view of fuel consumption, the efficiency of an engine is not given at the maximum of its power. The minimum unit cost per RPM is close to its maximum capacity, in the graph 80%. From that point on, as the ship's speed decreases, the amount of fuel consumed per unit of displacement increases. If RPMs increase above optimal capacity, the unit cost increases exponentially. On the other hand, these curves change depending on the weight of the boat and specific sea conditions. This behavior is independent of the size of the ship. The graph presents the fuel consumption curves as a function of the ship's speed. There are 5 curves, for different revolutions per minute, which are related to different blade pitches. The exponential nonlinearity is evident. The problem of supplying vessels to a rig is faced with operational planning arising in the offshore oil and gas industry, in which the routes and sailing speeds along those routes are determined for a set of platform supply vessels, PSVs, serving a set of delivery and/or pickup orders, so that costs are minimized. Navigation costs, mainly induced by the fuel consumption of PSVs, depend largely on the chosen sailing speeds. In addition, the fuel consumption and feasible speed ranges for PSVs are greatly affected by weather conditions that can vary over time, resulting in a weather-dependent vessel routing issue with route-dependent speed optimization. This problem is called the Speed-Optimized Time-Dependent Ship Routing Problem, TDVR-TSO. The decisions include the deferral of certain orders and the chartering of spot vessels, both associated with additional costs, corresponds to a mixed integer programming, MIP, model with the heuristic, adaptive large neighborhood search, ALNS. Computational tests in instances based on a real case of planning of the Norwegian continental shelf show that the model provides high-quality solutions. It is also shown that considering the speed and weather conditions optimization significantly improves solutions. The image shows fuel consumption, FC, as a function of time. In this case, a fixed speed change delta V induced by weather conditions is assumed for all sailing speeds, shifting the fuel consumption curve horizontally so that maintaining the desired speed V** becomes a considerably higher fuel consumption, with exponential growth. V min denotes the starting point of the speed range in which fuel consumption is a convex function of cruising speed. The TDVR-TSO determines the optimal cost-based trips, routes, for the PSVs being used, including a full schedule indicating navigation speeds and downtime or service required, on all navigation legs. It is also decided which orders to deliver and collect, and which to postpone, along with the decision of whether to charter spot vessels, on the spot market, in order to fulfill all mandatory delivery orders. The figure summarizes the solution process for TDVR-POS, listing the necessary input parameters and the decisions obtained, and how they can be categorized based on their characteristics. Initially, an academic case is presented. The wave height forecast is illustrated in the figure, where horizontal lines indicate the maximum permissible height, 4.5 meters, beyond which orders cannot be handled in offshore facilities, for safety reasons. The example problem considers orders placed by 5 installations. Each order is a mandatory delivery, MD, optional delivery, OD, or optional pickup, OP. Order sizes are given in containers. 2 contracted vessels, PSV-1 and PSV-2, are available, with a cargo capacity of 110 and 85 containers, respectively. For both boats, the allowable speed range is 10 knots to 14 knots, maximum sailing speed in good weather. The image presents a possible solution to the problem, in which all orders, both mandatory and optional, are fulfilled. The figure indicates the corresponding voyages of the 2 vessels and shows the sailing speed chosen for each leg. PSV-1 cruises at full speed to reach Facility 1 before closing at 10 p.m. The browsing speed remains relatively high until delivery has been made to the last facility, number 4. This happens to complete all cargo handling activities before weather conditions worsen on day 1. The day services are prohibited. On the last stretch of navigation leading back to the supply depot, the speed is reduced to a profitable minimum, as there is no risk of violating the permitted duration of the 3-day voyage. The northernmost journey is made by PSV-1. The blue positive numbers represent the pickup quantities, the negative, red, numbers represent the cargo deliveries. Real-world experiments consider Norway's oil production in the North Sea. For realistic instance generation, the offshore logistics network related to the Mongstad supply base, located on the west coast of Norway, was considered. Mongstad is one of the largest ports related to oil and gas-related activities in Europe, in terms of freight traffic, and 27 offshore facilities are served from this base. For each facility, an identification code, geographic location in terms of latitude and longitude, opening hours, and a standard order size are used to generate multiple test instances. Data associated with the 27 facilities in the case of Mongstad. Longitude, latitude, hours of operation, and standard order sizes are provided for MD, OD, and OP orders, respectively. Test instances used for computational study, grouped by the number of installations in each instance. There are 5 test instances within each group. The number of orders may vary, but the number of vessels in the fleet remains the same. Vessel chartering on the spot market is possible for all cases and in all groups. 4 meteorological states, WS, are considered based on significant wave heads, SWH, and the impact on PSVs in terms of forced speed reduction, delta V, as well as relative increases in service times, delta T serve, and fuel consumption, delta FS, I, for both service and idle time. The figure presents the weather scenarios, detailing the conditions experienced during the planning horizon. 5 test instances were randomly selected and solved for each of the 3 weather scenarios, with and without speed optimization. The design speed of 12 knots generally represents a reasonable balance between fuel efficiency and the service level of the order. For each instance and each weather scenario, the table shows the relative cost reduction achieved by including speed decisions, compared to the use of speed across all navigation legs. For the 5 test instances, the table presents the comparison when planning with and without weather forecasts, shows the costs incurred and the number of lost orders, #MO. The impact of weather planning is assessed for both scenarios, mixed rough and weather scenarios. The extra cost of planning based on a mental model, assuming it is fair, is significant, 62.33 and 71.58%. This is an indicator of the economic value of scientific planning. The image presents the algebraic formulation of the constraints of the TDVRP-SO model. Energy savings in train control optimization. The need for a clean environment is based on a rational consumption of energy. This covers all industries, and in general all human activities. Optimal train travel speed planning involves mathematical modeling to minimize energy consumption when the train has a predefined maximum arrival time. First, it must be considered that all industrial processes are variable speed, and that energy consumption, depending on the speed of the process, is nonlinear, it is exponential. This implies that, in the absence of economies of scale, the regulation of the speed of industrial processes is fundamental in the process of controlling energy consumption. Production facilities do not have a defined capacity, it is set according to the speed of the process, and the time that this speed lasts. That is a decision variable of industrial operations. The table presents the energy consumption versus speed of the AB 103 high-speed train. The column 2 shows the kWh consumed per kilometer for 3 speeds analyzed. The nonlinearity is noticeable. As a vehicle increases its speed, when it is operating above its maximum efficiency, the unit amount of fuel consumed increases, which implies higher variable costs. However, increased speed means increased production capacity, which lowers investment costs due to increased vehicle use. The optimal decision is not obvious. The train control optimization involves several steps. These are: vehicle's energy demand, vehicle's energy balance, substation's energy balance, braking energy use, supply system measures, and further approaches. Several of them involve mathematical optimization processes. The paper Optimal Trajectory Planning for Trains Using Mixed Integer Linear Programming presents a mathematical model that includes, in detail, the resistance of the route, such as slope, tunnels, and curves, and arbitrary speed restrictions. The objective function is a weighting between energy consumption and driving comfort, but it could be minimizing the cost of energy. The nonlinear function of energy consumption versus velocity is represented by a piecewise linear function. The optimal control problem is formulated as a mixed integer linear programming (MILP) problem, which can be efficiently solved by existing solvers. The case study considered 2 cases. For the first one, the total running time equal to 5.25 minutes, indicated by T1, black solid line, while for the second case is 10 minutes, indicated by T2, red dashed line. The speed of the train is presented in Figure 1. The optimal reference trajectories and the tensile and braking forces applied are shown in Figure 2. The energy consumption with running time T2 is lower than that with running time T1, but at the cost of a longer travel time. Figures 3 and 4. It is worth to note that the computation cost is very low for this MILP approach, is less than 10 minutes in 2011, Today the algorithm must be, at least, 1,000 times faster. The figure, extracted from another study, presents the relationship between the energy consumed and the travel time. The nonlinear behavior of the function is evident. The train journey can be modeled as an interleaved sequence of three states. Braking, when the train slowed down, eliminating energy consumption or recovering previously consumed energy, which can be used later, green line. Dwelling, when the train maintains a constant speed, minimizing energy consumption, and accelerating, when speed is increased, and energy is consumed according to the situation, red line. Railway alignment optimization. Railways are threatened by geological hazards whose disastrous effects include severe economic losses as well as serious casualties. It is vital to properly consider such dangerous geological impacts during a railway alignment optimization process. However, geological factors are complex, especially in mountainous regions. In addition, economic factors are also crucial in the design of the railway alignment. Therefore, optimizing railway alignment can be termed a bi-objective cost-risk decision-making process. Truck speed modeling is very important in long-range travel. In state-of-the-art cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capacity from the nearby environment. This autonomous capability may be called optimal short-range control. However, there is another level of vehicle operations planning that is long-range, and related with the total journey. The problem of optimizing energy consumption, gasoline, diesel, natural gas, propane, or electricity, is complicated because the energy function is nonlinear, and depends on factors that are the result of the decision-making process, such as the load and the position of the truck in any moment. Additionally, exists exogenous factors that define fuel consumption, depending on the vehicle and the route. These may be divided into static, for example, slope, rugosity, etc., and dynamic, that depend on traffic and route weather status. High can incorporate the modeling of the speed of the vehicle, as one of the decision variables of the routing model. The fundamental idea is, that the arrival time is the result of coordinating time windows, and fuel consumption, so as to minimize the cost of fuel throughout the total journey. In this way, the truck will arrive just in time, not a minute before or one after. Emissions estimation in multimodal transportation. Ports play a key role in fostering the growth of trade and national and international economies. As ports continue to expand in size and capacity, the impact of their operations on air quality and climate change becomes increasingly significant. While nearby regions may experience economic benefits, there are significant concerns regarding the emission of air pollutants, which have adverse effects on both human health and climate change. Predictive modeling of port emissions is a valuable tool for identifying areas of concern, assessing the effectiveness of emission reduction strategies, and promoting the sustainable development of ports. The main objective is to estimate SO2 emissions from ships during various port activities, including hospitality, maneuvers and cruises. The objective is to obtain information about emission patterns and explore strategies to mitigate their impact. The article, Towards Cleaner Ports, Predictive Modeling of Sulfur Dioxide Shipping Emissions in Maritime Facilities Using Machine Learning. It contains the case presented below. Emissions estimation in multimodal transportation. Ports play a key role in fostering the growth of trade and national and international economies. As ports continue to expand in size and capacity, the impact of their operations on air quality and climate change becomes increasingly significant. While nearby regions may experience economic benefits, there are significant concerns regarding the emission of air pollutants, which have adverse effects on both human health and climate change. Predictive modeling of port emissions is a valuable tool for identifying areas of concern, assessing the effectiveness of emission reduction strategies, and promoting the sustainable development of ports. The main objective is to estimate SO2 emissions from ships during various port activities, including hospitality, maneuvers and cruises. The objective is to obtain information about emission patterns and explore strategies to mitigate their impact. The article, Towards Cleaner Ports, Predictive Modeling of Sulfur Dioxide Shipping Emissions in Maritime Facilities Using Machine Learning. It contains the case presented below. Emissions estimation in multimodal transportation. Ports play a key role in fostering the growth of trade and national and international economies. As ports continue to expand in size and capacity, the impact of their operations on air quality and climate change becomes increasingly significant. While nearby regions may experience economic benefits, there are significant concerns regarding the emission of air pollutants, which have adverse effects on both human health and climate change. Predictive modeling of port emissions is a valuable tool for identifying areas of concern, assessing the effectiveness of emission reduction strategies, and promoting the sustainable development of ports. The main objective is to estimate SO2 emissions from ships during various port activities, including hospitality, maneuvers and cruises. The objective is to obtain information about emission patterns and explore strategies to mitigate their impact. The article, Towards Cleaner Ports, Predictive Modeling of Sulfur Dioxide Shipping Emissions in Maritime Facilities Using Machine Learning. It contains the case presented below. The analysis was conducted for the Port of Barranquilla, Colombia. The dataset used for this analysis was obtained from General Directorate of Maritime, which is a Colombian authority in charge of organizing, coordinating, and controlling maritime operations in the country. The image shows the list of the variables in the dataset. The table shows an example of the data after transformation. The table shows preview of dataset after label encoding. The table shows the original data before transformation. The diagram shows the process of a methodology for predicting emission inventories. Artificial neural networks, linear regression, gradient descent, and automated machine learning. Automated machine learning, AutoML, is a term used to describe strategies that automate the process of identifying high-performing models for predictive modeling tasks with very low human intervention. One notable Python-based open-source library for AutoML is TPOT. TPOT combines the popular scikit-learn-ML package, which includes data transformations and ML algorithms, with a genetic programming stochastic global search technique. The table presents the hyperparameters of the TPOT model. The table shows the hyperparameter experimentation using TPOT regressor. The table shows the results of linear and nonlinear regression. Transshipment operations in intermodal terminals. The article, Modeling Carbon Emission Estimation for Hinterland-Based Container Intermodal Network. It contains the case presented below. To address growing environmental challenges, the analysis of high-carbon transport systems seeks to achieve carbon peak and carbon neutrality goals, calculating the carbon emissions estimate and identifying carbon reduction drivers for the inland-based intermodal container network. The impact of transport vehicles on climate change is often analyzed from the well-to-wheel (WTW) perspective, consisting of two phases, well-to-tank (WTT) and tank-to-wheel (TTW). WTW is a life cycle evaluation mode developed for transport fuels and energy carriers that cover resource extraction to vehicle operation, excluding the vehicle's life cycle. In the TTW mode, electrical energy is estimated to be zero carbon emission. In the existing studies on intermodal emissions, there are few works that distinguish between the two emission modes. Well-to-wheel, WTW, and tank-to-wheel, TTW. Taking the port of Shanghai and the Yangtze River Delta as a case, carbon emissions from the last 10 years are used for well-to-wheel, WTW, and tank-to-wheel, TTW, modes. The critical factors that drive sensitivity analysis and the variation of carbon emissions in different scenarios with carbon reduction policies are identified. The results indicate that the transport structure and fuel choice significantly affect the reduction of grid emissions. In the current policy-based scenario, WTW mode peaks carbon between 2030 and 2035, while TTW mode peaks earlier. The hinterland-based container intermodal network is based on the transport network among ports and hinterlands. And this network depends on the freight flow in different periods. Within the network, containers move along the intermodal chain between ports and destinations through intermodal nodes and vehicles. To reduce the complexity of the network, the following definitions and assumptions were made. The intermodal transport network is based on the freighted flows between nodes. Any node in the network may be an origin of freight flow. The network estimation model of carbon emission evaluates the carbon emission for each specific period, and the hinterland transportation of containers includes roads, inland waterways and railways. The last mile distribution depends on road transport. The carbon emissions estimation model of the intermodal network is developed in two stages, including transport and transfer. The freight flows model to obtain the container freight flows from the port to nodes. Then combined flows with the carbon emission estimation model to obtain the carbon emission of the network. The model can be used to estimate carbon emissions in a regional intermodal network by using each node in the region as a flow sending point and repeating the above calculation steps. The figure shows the flowchart of the math model. The figure shows the container transport process in the intermodal transport network. On the one hand, the container transshipment operations include loading and unloading operations and horizontal transport operations, which vary depending on the different terminals. Trucks can usually transfer in port directly, while transshipment of trains and ships depends on the infrastructure of port to consider whether it is possible to transfer directly, or else they must be connected by trucks for short connections. On the other hand, the model also consider the energy consumption of transport vehicles during container handling assistance, such as ships in the port, transport vehicles waiting in queue and locomotive traction. The image partially shows the carbon emissions estimation model. The map shows the intermodal transportation network in the Yangtze River Delta, YRD, which is the junction of three sub-networks, waterways, railways, and roads. The complexity of the carbon emission estimation model leads to results parameters required for the model, and uncertainty in the parameters can affect the value and of the multimodal network estimation. The main uncertainties in this study are the container flow ratio and container weight of the freight flows forecast, vehicle activity efficiency, energy efficiency, transshipment efficiency, and port operation. To discuss the impact of uncertainty, we analyze the impact of different parameter changes on the overall carbon emissions. Using container flows data in 2020 as the baseline value and identify the critical driver factors affecting the network carbon emissions. The table shows the attributes of the transport vehicle. The tables show equipment operation data for nodes, and carbon emission factors and net calorific values for different types of fuels. The map shows the distribution of container flows for the 2020 case network. The table shows the aggregate results for each mode of network. The map shows the distribution of carbon emissions distribution from the case network in 2020. The transfer of 10% of container flows from road transport to rail and water transport at the same time can bring 153,600 tons of carbon emission reduction, accounting for 8.4% of the total emissions in 2020. Rail and water transport have the share of container flows and low carbon intensity in the current network, which indicates that there is still considerable potential to adjust the existing transport structure for emissions reduction. The image shows the aggregate structure of the case data and the results. The image shows the sensitivity analysis of the key parameters. The increase of transit efficiency is more sensitive in both estimation modes. The sensitivity factor for the WTW mode in 2020 is 4.6%, with a 10% increase in efficiency resulting in a decrease in carbon emissions, accounting for 0.5% of total carbon emissions, and 9.3% of transit emissions in 2020. It is followed by an improvement in the proportion of ship-truck direct transfers, with a sensitivity factor of 0.1%. Therefore, improving the overall efficiency of the transfer nodes and optimizing the truck-ship transfer operation have an important effect on the carbon emission reduction in the transfer process. Based on the sensitivity analysis above, even the best way is to improve the truck energy efficiency to reduce the carbon emission. It's not easy for carriers to choose that because of the decreased engine efficiency and higher maintenance costs. In contrast, shifting road transport and container loading are better choices for the transportation department. The critical driver factors according to the operability of the transport sector and intermodal companies on emissions reduction was ranked as follows: shifting of road transport to rail and road, increasing container weight, applying clean energy, improving truck energy efficiency, and improving transfer efficiency. To analyze the impact of emission reduction policies on CO2 emissions, the driver factors mentioned was grouped into 4 categories as follows. Transport restructuring, W1. Clean energy application, W2. Energy efficiency for transport vehicles, W3, and transfer technology upgrading, W4. The table shows the sensitivity analysis parameters toward the cases. The table shows the carbon emission results for different scenarios for the 2 modes, WTW and TTW. The graph shows the trends in carbon emissions for the different scenarios. The graph shows the distribution of case data and results for 2035 in Scenario 2 with WTW mode. Road transport and its carbon emissions continue to account for a significant part of the YRD network, accounting for 59.3% of container flow and 76.27% of total carbon emissions in the network, respectively. Diesel consumption, 92.07%, remains the main contributor to energy consumption. Rail intermodal transport, which has the lowest carbon intensity in the network, does not feature prominently in the YRD network due to the poor transfer process and a small proportion of freight transport. The transition of transport structure and fuel options significantly affects the overall reduction in emissions, followed by the weight of containers. This study takes the port as the intermodal hub and establishes the intermodal container network based on the port container flow. Through the process analysis, was discussed the carbon emission model of multimodal transport based on the transport and transfer processes. 2 models was developed. A hinterland-based carbon emission model for multimodal transport network, and a network flow distribution model to evaluate the carbon emission of the intermodal transport network. Road transport and its carbon emissions continue to account for a significant part of the YRD network, accounting for 59.3% of container flow and 76.27% of total carbon emissions in the network, respectively. Diesel consumption, 92.07%, remains the main contributor to energy consumption. Rail intermodal transport, which has the lowest carbon intensity in the network, does not feature prominently in the YRD network due to the poor transfer process and a small proportion of freight transport. The transition of transport structure and fuel options significantly affects the overall reduction in emissions, followed by the weight of containers. Based on the current policy scheme, the YRD network will peak in 2030 to 2035 with 2 million tons of CO2 in the WTW mode. TTW mode will peak earlier than WTW mode in 2030. The total carbon intensity is 0.1343 tons of CO2 per container, a decrease of 32.5% compared to 2020. The efficiency of the operation of the equipment, and the organization of transit between vehicles and vessels, have a significant impact on carbon emissions. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.